Dear third grade students, first of all, blessed Ramadan for you, your beloved people, and all Muslims around the world. In accordance with the decrees of the Supreme Council of Universities, this is the last recorded lecture for the course entitled Computer Applications in Management and Economics. I continue lecturing you in the economics part. Economists are often interested in exploring the nature of the relationship between different economic variables. Socioeconomists are involved in studying the link between economic and social variables. For example, they may investigate the association between the increasing number of crimes and the increasing number of unemployed people. Furthermore, firms are often concerned with examining the relationship between sales and advertisement expenditure. Moreover, policymakers are likely to be interested in exploring the association between interest rates and inflation. Hence, we could say that studying the relationships between economic variables is an important topic. In the current presentation, we are interested in studying the relationship between two variables. We could describe this relationship using three ways. First, the graphical method could be used to describe the link between the two variables. I mean, we can use the scatter diagram in this regard. Second, we can compute the correlation coefficient to numerically quantify the relationship between the two variables. Third, we can estimate a simple regression model in which we regress the dependent variable in the regressor using the ordinary least squares method. You are already familiar with these techniques from the previous statistics courses. A scatter plot is simply a graph in which the values of the first series are plotted against the values of the second series. Note that the values of the independent variable are represented by the horizontal axis, whereas the values of the dependent variable are represented by the vertical axis. A scatter plot includes a cluster of dots that represents all pairs of data points. Intuitively, if dots of a scatter plot display a general upward slope, then the two variables are positively correlated. On the other hand, if these dots display a general downward slope, then the two variables are negatively linked. Furthermore, if these dots are widely scattered, then we could say that there is a weak link between the two variables. In contrast, if these points are less scattered, then we could say that there is a strong association between the two variables. Now, let's consider two examples for scatter plots. For the first example, we consider the scatter plot that shows the relationship between our money supply and the price level for the US data, which we have employed many times during the current course. The screenshot 6.14 in your textbook, which is shown in the current slide, displays the scatter plot for the relationship between these two variables. You could easily detect that data points have an upward slope. Moreover, you can easily realize that data points are less scattered over the entire plot. Thus, we could say that the two variables seem to be strongly and positively linked. Note that the regressor is represented by the horizontal axis, whereas the dependent variable is represented by the vertical one. Now let's consider another example using the screenshot 6.17. It shows the scatter plot for the lot size and their sale prices for a cross-sectional dataset of houses sold in Canada during the year 1987. Again, remember that the regression is represented by the vertical axis, whereas the regressor is represented by the horizontal axis. You can easily identify the positive relationship between the two variables, given that data points have an upward slope. In other words, houses with large lots tend to have large sale prices, and vice versa. Note that the association between the variables shown in the previous slide is stronger than that shown by the current screenshot. This is because the data points in the current scatter plot are scattered over a wider plot area. Kindly note that these screenshots illustrate an important aspect of thinking about correlation. That is, correlation tells us how well a straight line can be fit through a scatter plot. Strongly correlated variables are close to a straight line. On the other hand, weakly correlated variables are more scattered over the area. Refer to the screenshot 6.16 in your textbook that shows the scatter plot for the relationship between the average hourly wages and unemployment rates. Test yourself by answering the following questions. Could you identify whether the two variables are positively or negatively correlated? Does this relationship agree with prior expectations? Is this relationship strong or it is weak? And why? Scatter plots can be employed to visually explore the relationship between variables. As you already know, it graphically shows the relationship between two variables in which the values of the dependent variable are plotted against the values of the independent variable. Thus, to plot a scatter graph, the two variables have to be saved in a group. If not, you first have to create a group to contain the variables of interest. You already know how to create a group from chapter 2. Other ways to create a group are described in chapter 6. You can refer to them. Double-click on the group of interest to open it. From the group title bar, select View menu. From the drop-down menu that appears, select Graph to bring the Graph option dialog box that is displayed in the current slide. Under the middle section named Graph Type, select Basic Graph from the General option and select Scatter from the specific options as illustrated in the screenshot 6.13. Then click the OK button. These are the steps we followed to plot the scatter graph that shows the relationship between the US data of narrow money supply and the price level. Now, a relevant question might be how to graph the scatter plot that includes a regression line as depicted in the screenshot 6.17. This screenshot shows the relationship between the sales price of houses and their lots in a sample of Canadian houses as mentioned earlier. Let's show how to do so in the next slide. To obtain a scatter plot with a regression line, We follow the same steps as before, but with an additional step. Let me explain. We first double-click on the group that contains the variables under consideration to open it. Then we select the View menu to obtain the sub drop-down menu, which we showed in the previous lecture. Then we select Graph to bring up the Graph Options dialog box that appears in the current slide. Again, and as before, we use the middle section where we select a scatter. Moreover, we use the right-hand side section entitled Details. Under this section, there is an option named Fit Lines, which has a button that includes a number of options, from which we select a gradation line. Note that we highlight this button with the selected option using yellow color. Then hit the OK button to obtain the required scatter plot with the fitted regression line. Graphical representation of the relationship between variables is an important way to visually identify the direction and the strength of the association between variables. However, we need a numerical measure that helps us to quantify the strength of such a linear relationship. As you already know, such a numerical measure is termed the correlation coefficient. It is a statistical measure helps to numerically quantify the strength of the linear relationship between variables. I mean numerical variables because in the current course we are interested in studying numerical variables. From figure 6.1, we could say that its values always lie between -1 and +1. Positive values of the correlation coefficient imply the existence of positive correlation between the two variables under consideration, and vice versa. The closer its value to 1, the stronger the linear association between the two variables of interest, and vice versa. Now, let's show how to compute it using e-views. To compute the coefficient of correlation between two variables or more, you must save the variables under consideration in the same group. Then you double-click on the group of interest to open it. From the group title bar, select View to get the sub drop-down menu, and from which select Covariance Analysis to bring the dialog box displayed in the screenshot 6.18, which is displayed in the current slide. Under the upper left section of this screenshot named Statistics, select Ordinary for the method, which is highlighted using the yellow color. Then take the box next to Correlation as shown. Finally, click the OK button to bring the correlation matrix. We followed these steps to compute the correlation coefficient between the narrow money supply and the price level for the US data. Their correlation matrix is displayed in the screenshot 6.19, which is shown in the next slide. Screenshot 6.19 shows the correlation matrix between the US narrow money supply and its price level. Note that the correlation coefficient in the diagonal is 1. This is because it represents the relationship between the variable and itself. The correlation between M1 and PR is strong and positive. Actually, it's very close to 1, confirming previous conclusion made when discussing the scatter plot displayed by the screenshot 6.14. It is worth mentioning that the correlation coefficient between M1 and PR is exactly the same as the correlation coefficient between M1 and PR, which is 0.98. This conclusion is in line with the quantity theory of money, which predicts that money supply and the price level are positively correlated. We repeated the same steps to obtain the correlation between lot size of some Canadian houses and their sale prices. The screenshot 6.20 shows the correlation matrix between these two variables. Note that, as mentioned earlier, correlation coefficients across the diagonal is equal to 1. The correlation coefficient between the lot sizes of houses and their prices equals to 0.535. That is, it is positive, but it's weaker than the correlation between money supply and the price level for the US data. This confirmed the conclusion we made when exploring their scatter plots during the current lecture. Now it's your turn to comment on the correlation matrix showing the relationship between the average hourly wages and unemployment rates. This correlation matrix is shown by the screenshot 6.22. Sample regression could be illustrated using graphical intuition. Let's reconsider the scatter plot displayed in the screenshot 6.17, which plots lot size of some Canadian houses against their sale prices. Examination of this scatter plot reveals important information about the relationship between the sale price and the lot size of these houses. The straight line drawn through these points on this plot offers an informative summary of the relationship between these two variables. The main task of regression is to formally analyze this relationship. In other words, we want to estimate the best fitting regression line to the data points in which we obtain numerical values for the slope of this line and the intercept. Let's briefly resume what is meant by the best fitting line. First, we assume that a linear relationship between the sales price and the lot size exists. Let's call the sales price Y and the lot size X. The linear relationship between Y and X could be expressed by equation 7.1, which is known as the mathematical model for the regression line. Remember that a mathematical model assumes that the relationship between variables is exact. In equation 7.1, Y is the dependent variable, whereas X is the regressant. The intercept of the line is beta 1, whereas beta 2 is the slope of the line. Beta 1 and beta 2 are the unknown parameters to be estimated. However, in the real world, we would never expect that all data points lie precisely on the straight line. Refer to the screenshot 6.17 in the previous slide. Other factors which are not included in the model make individual data points lie close to the straight line but not exactly on it. Therefore, we could say that the linear regression model is always an approximation of the true relationship between variables under consideration. Thus, we could rewrite equation 7.1 as shown by equation 7.2, where we introduce the error term. This error term represents the deviation between the true observed value of the dependent variable y and its estimated value that lies on the straight line for the population. As you already know from statistics courses, we don't study the whole population, but in practice we study the sample to estimate the values of the unknown parameters beta 1 and beta 2. The econometric model of the sample is highlighted in yellow. In this model, U is known as the residual, which represents the deviation between the true observed value of the dependent variable y and its estimated value that lies on the straight regression line for the sample. In the econometric model of the sample, we compute the estimates beta 1 hat and beta 2 hat in a way that provides a straight line through the points in the scatter plot which fits best. Thus, it's important to define what's meant by best fitting line. Let's use figure 7.1 to explain this issue. Assume that we have only 3 data points, which are A, B, and C. From geometry, we can draw one and only one straight line connecting any two separate points. However, there are 3 data points in the attached figure. Thus, we are not certain about what is best fitting line. The line drawn in this figure passes through none of the 3 points. In other words, each point doesn't lie exactly on the straight line. Hence, we get 3 residuals that are U1, U2, and U3. These residuals are measured by the vertical distance between an observed data point and the straight line that are highlighted using the yellow color. The best fitting line must have small residuals. To obtain the best fitting line, residuals sum of squares, which is given by equation 7.5, must be minimized. For this reason, estimates computed in this way, beta 1 hat and beta 2, are termed ordinary least squares estimates. EViews and other software packages can easily compute values for beta 1 hat, beta 2 hat that minimize the residual sum of squares. In addition, such software packages compute the coefficient of determination that informs us about goodness of fitting the regression model. Now, let's explain how to run a simple regression using EViews. We now use the quick menu from the main menu to estimate a sample regression model for the sale price of the Canadian houses under consideration. Click the quick menu from the main menu to bring the drop-down menu that is depicted in the left-hand side of the current slide. Select the estimate equation option, which is highlighted using the yellow color. By doing so, the equation estimation dialog box appears. Under the section named equation specification, type your dependent variable followed by C and then type your explanatory variable. Each is followed by space as shown by the screenshot 7.2. Under the estimation settings section, make sure that the LS least squares is selected. It is worth mentioning that it is selected by default. Then hit the OK button to obtain the regression results that are displayed in the screenshot 7.3, which is shown in the next slide. The screenshot 7.3 represents a typical views output for a regression. This typical output consists of three panels or sections, namely the top panel, the middle panel, and the bottom panel. Screenshot 7.5 depicts the top panel of the sample regression model displayed by the screenshot 7.3, whereas screenshots 7.6 and 7.7 show the middle and the bottom panels respectively. The top panel provides information about regression inputs. This general information includes the dependent variable, method of estimation, date and time of estimation, sample and included observations. Note that the dependent variable is the sales price and the estimation method is the least squares. The middle panel summarizes information about the estimated regression coefficients. It provides the information about the estimated intercept, which is termed here C, symbolized by letter C, and the estimated slope coefficient. Information provided includes the value of these coefficients, their corresponding standard errors, t-statistics, and their accompanied p-values. These details are important when performing hypothesis testing relating to OLS estimates. Table 7.2 provides some details about the elements of this middle panel. Finally, the bottom panel provides summary statistics relating to the entire regression. As shown in the screenshot 7.8 and table 7.3, these summary statistics include inter alia, R squared, that is the coefficient of determination, F statistic, and its p-value. Note that this output is to be included in the appendix of your research paper or report. Thus, a relevant question might be how to report your regression results to be included in the discussion section of your report. Let's show that in the next slide. Then we will interpret the meaning of the OLS estimates and the overall significance of the estimated model. There are various ways of reporting the results of regression analysis. However, we will use the attached format to report our results. First, we write the regression equation. In the current example, the dependent variable, that is sale price, equals the estimated numerical value of the intercept, which is highlighted using the light blue color, plus the estimated numerical value of the slope coefficient, which is highlighted using the green color, times its corresponding regressor, which is the lot size variable. Figures in the first set of parentheses are the estimated standard errors of the regression coefficients. As you already know from statistics courses, standard errors are statistical measures that inform about the reliability of the estimates. The larger the standard errors, the less precise are the estimates. Figures in the second set are estimated t-values computed under the null hypothesis that the true population value of each regression coefficient individually is 0. Views automatically reported the computed t-statistics and its computed p-value of observing the t-statistic given that the coefficient is equal to 0 under the null. Thus, figures in the third set of parentheses are these p-values, which are highlighted using the yellow color. Then we report the value of the coefficient of determination, that is the R squared, and the computed F statistic and its p-value. Finally, the sample size is to be reported as shown. Now, let's interpret our results. The estimated slope coefficient beta 2 hat can be interpreted as the marginal effect of x on y. In other words, beta 2 hat is a measure of how much the regressor influences the dependent variable. That is to say, it measures by how much the dependent variable tends to change if the regressor is changed by 1 unit. The definition of unit is determined by the dataset being examined. In the current example, the selling price is measured in Canadian dollars, whereas the lot size is measured in square feet. Thus, we could say that an extra square foot of lot size is associated with an increased price of around 6 Canadian dollars and 59 cents. The estimated intercept of the regression model, which is beta 1 hat, usually has little economic interpretation. Thus, and in many cases, it will not be examined or discussed, The coefficient of determination, that is termed R squared, is a measure for the goodness of fit of the fitted regression line to a data set. It is a numerical measure for the goodness of fit that informs how well the sample regression line fits the data set. Its values lie between 0 and 1. It equals 0 if the regression line does not have any explanatory power in explaining variation in the dependent variable. In contrast, if the regression line perfectly fits the data points, then the R squared equals 1. For the current example, the model explains about 28.7% of the variation in the sales price. A relevant question is that, is it likely that our results could have been generated by chance? Let's answer this question in the next slide. As you already know from statistics, we could answer the previous question through performing hypothesis testing. Fortunately, if you reported the p-value for computed t-statistics and f-statistic, and thus we could easily decide whether our results are significant or not. Let's use the 5% level of significance. Given a p-value, we can at a glance decide whether to reject or not reject the null hypothesis that the true value of a regression coefficient is 0 against a two-tailed alternative that it differs from 0. If the p-value of the computed t-statistic is less than the 5% level of significance, we have to reject the null hypothesis that the coefficient of interest equals 0. Now we have to compare the 5% level of significance with the reported p-values for each individual coefficient to decide whether to reject the null that the estimated coefficient of interest equals 0 or not. Given that the p-value for the t-statistic of the intercept equals 0, which is less than the 5% level of significance, then we have to reject the null hypothesis that the estimated intercept equals 0. Similarly, the p-value of the computed t-statistic of the slope coefficient, which is 0, is less than the 5% level of significance, we must reject the null hypothesis that the estimated slope coefficient is 0. Therefore, we could say that the lot size of the house significantly affected the house price. Regarding the coefficient of determination, that is the R-squared, if the regression line perfectly fits the data points, then R-squared equals 1. In contrast, of R-squared equals 0, this means that the model doesn't have any explanatory power in explaining variation in the dependent variable. To test the null hypothesis that R-squared equals 0 could thus be interpreted as the test of whether the regression explains anything at all. The p-value of the computed F statistic is less than the 5% level of significance, indicating that the F calculated is significantly larger than its critical value. Thus, such a pattern of the relationship between the sales price of houses and their lot sizes has not occurred by chance. So, the regression model has an explanatory power of explaining variation in the sales price. This is the end of our lecture. Thank you and good luck.